Hi guys, in this video report we're going to be discussing the assignment for types of matrices. Most of these questions have been asked repeatedly in previous years, so consider this video important. Okay, let's get started. The first question is, for what values of A is the following matrix symmetric? Now, for this question, the only thing that you need to recall is that symmetric matrices in general are defined by Aij is equal to Hij. And when you are solving this question, then you use that for not just A12 is equal to A21, but also for A23 is equal to A32. You use it for all the ones for which it is possible to narrow down on the value of A. So, as you can see here, let me just erase ink. You have A12 is equal to A21. When you equate A squared minus 1 with A plus 1, the two values of A that you're left with are minus 1 and 2. Okay. However, when you do A23 is equal to A32, the only value of A that you get is A is equal to 2. So this means that after these two steps, you can reject A equal to minus 1 and you can actually get A equals 2 as your final answer. Now, the next question is that you have to show that any square matrix A can be uniquely expressed as the sum of a symmetric matrix B and a skew-symmetric matrix C. There are two things to pay very careful attention to here. One is that they are asking you to also say uniquely, which means that you have to prove the uniqueness as well. And the second thing is that this question has a learning step. Once you understand and remember that learning step, everything else is pretty much a manipulation game. So the learning step is this precisely. You have to actually define B and C in a particular manner so that you can solve this question. Now B we are defining as A plus A transpose upon 2, whereas C is A minus A transpose upon 2. Remember this, everything else will make sense. So the first thing that you need to do is prove that B and C are actually symmetric and skew-symmetric respectively. For this, let's say you consider B transpose, which is A plus A transpose upon 2 transposed. Recall that the transpose has no effect on the constant, so you simply have 1 upon 2 A plus A transpose transposed, which is equal to 1 upon 2 A transpose plus A transpose transposed, and the transpose of a transpose is the matrix itself, as you would recall from the rules of transpose. So you just are left with 1 upon 2 A plus A, A transpose plus A, which in itself is actually equal to B. So here, because B transpose is B, you can say that B is a symmetric matrix. Similarly, for C transpose, what you have is A minus A transpose upon 2 transpose, which is equal to 1 upon 2 A transpose minus A transpose transposed, which is equal to 1 upon 2 A transpose minus A, which is equal to minus 1 upon 2 A minus A transpose, which is equal to minus C. So C you can say is skew symmetric. Okay. Now you get to the uniqueness aspect. First of all, let me decrease all ink on slide. Okay. Now you get to the uniqueness aspect, which is for you to prove that B and C are unique in their representation of A. So for this, what you do is let A be equal to M plus N, where M is any symmetric matrix and N is any skew-symmetric matrix. Now you need to prove that M is equal to A and N is equal to B. The first thing that you need to, write out is that A is equal to M plus N. This is what you assume, right? And you know that M is symmetric, so that means M transpose is equal to M and N transpose is equal to minus N, because M is symmetric and N is skew-symmetric. This means A transpose is actually equal to M transpose plus N transpose, which is equal to M minus N. So now you have two equations. This is the first equation. This is the second equation. When you do 1 plus 2, what you have is A plus A transpose is equal to 2M, which implies M is equal to A plus A transpose upon 2, which is equal to B. Similarly, when you do 1 minus 2, what you have is A minus A transpose is equal to 2N, which implies N is equal to A minus A transpose upon 2, which is equal to C. So there you have it. You have the values of B and C, and you've proved that they are unique. Okay. Now we come to another very important question where you have to consider the following matrix: A is equal to I minus x into x transpose x inverse x transpose. You don't need to remember the question, in terms of remembering the matrix itself, but this is an important question. So, let's see what kind of questions are generally asked. The first question that you were asked is, must A be square? Now, the reason that I've put the answer here is because while I will also explain it, this is also something that, you can't mess up your words in, because this is a 2 marker or a 3 marker. If you don't put in everything that is required, you are very likely to lose all the marks, even though your logic is correct. So the first question is, must A be square? Here clearly you can see that A is the answer of a subtraction from an identity matrix. An identity matrix by its nature is square. So because A is going to be something that is the answer to this subtraction, and in subtraction you need the same dimension, therefore A has to be a square matrix. This is what it logically makes sense, and this is how you would put it. The second question is, must x transpose x be a square matrix? Now again, this is very logical, that because you're calculating the inverse of x transpose x and you want this matrix to exist, x transpose x needs to be a square matrix, because inverse can exist only for a square matrix. Okay, the next question is, must x be square? So here when you look at it, it is x into x transpose x inverse x transpose. Consider x to be an m cross n matrix. And let's just write out the dimensions of each of the following. So you have m cross n cross m cross n, and n cross n. Okay. Now you can clearly see that this multiplication is possible. Actually, before that, let's just see this multiplication. So you can see that this multiplication is possible because you have m cross m here. So this will become common and you would be left with n cross n, which means that this matrix inside the bracket is going to be a square matrix, which is what you needed. So the first condition is met here. Okay, then what is left is m cross n cross n, and n cross n. Now you can look at this and you would have m cross n, and then you would be left with n cross m. Again, this multiplication is possible. You're left with an m cross n matrix, which is a square matrix, which is what you wanted. So clearly, the fact that x is a non-square matrix doesn't really, hamper anything here. So x can be a square of a non-square matrix. Again, the way to show it is like this. First, concentrate the bracket here, because this needs to be square, and then the answer needs to be square because you just argued that. Okay. Now the last part of this question is to show that A is as a matrix is idempotent. Recall that idempotence just means that A square is actually equal to A. Okay. Now the reason that I've put the steps here is because I would like you to be able to go back to this proof in case you need it. And sometimes it does get a little confusing when it's not written out clearly. So let's just go here step by step. So A square is equal to A into A, right? Just write out the A matrix. Now after this step, you can see that this is A minus B into A minus B, which is the identity of A minus B whole square, which is A square minus 2AB plus B square. Now A square is just going to be I square. I square is just I because it's like 1 squared. So and in case this is something that is not very intuitive to you, work it out. You will see that it's the matrix itself. Then you have minus 2AB. I have just flipped the order here, and you can do it because it's the identity matrix, but generally you shouldn't. The I should have been written here. But in any case, any matrix multiplied by I is the matrix itself. So you are left with just this matrix right here, plus B square, which is the square of this term right here. Now the first thing to notice in the square of this term is that you have x transpose x inverse here, and you have x transpose x here. So recall that A inverse times A is actually equal to I, because that's how you define the inverse. Okay, so you have I minus 2 into this term right here, plus x transpose x inverse x transpose x, which can become another I. So I just done this substitution here, and then I times any matrix is the matrix itself. So you are left with this particular term twice and plus this particular term again, because the I gets goes away. What you're eventually left with is just I minus this particular term right here, which is exactly equal to the matrix A. So you've proved successfully that A square is actually equal to A. Okay, I would suggest working this out on your own once as well. It's not difficult, it is just involves a little bit of manipulation. Okay. Now the last question that we come to is that suppose that you're given PQ is equal to Q squared P, then you're supposed to prove this right here. Now, my suggestion with any such question is to write it out very simply. So PQ is equal to Q squared P is what you're given. Okay. PQ square is going to be PQ into PQ, which is equivalent when you substitute is into Q square P into Q square P. Now, the first thing, again, you would like to substitute again because you want to get Q's, at a higher power. So you can write this out as something like PQ into QP. So you would have Q square P, QP, which is equal to Q to the power 4, PQ into P. So which is equal to Q to the power 4, Q square P into P, which is equal to Q to the power 6 P square. So you have proved it. Now, this is a cleaner version of what we've just done. And it's just the same steps, just written out a little more clearly. This brings us to the end of this video. I hope things are clearer to you. Thank you.